Right, thank you very much. Thank you to all speakers. I'm gonna make a small change, Colin Gentleman, what I said before. I had said I'm gonna mute you all and then I mute selectively whoever has a question, but given that we've got like 140 participants, it'll take me forever to sort through all the windows and find the right one. So I'm gonna unmute you all, and then maybe you can mute yourself, and then unmute yourself when it's your turn to speak. Maybe that'll be a more efficient way to do that. So, do we have any questions?
Sure, I'll jump in. Camille, it's nice to see you again. Beautiful presentation, and
thank you.
Also enjoyed yours. On the last point about the validation, can you comment a little bit more about how you view that the human electrophysiology could validate that? Do you mean with laminar recordings in intracranial patients?
Yes. So obviously it's very difficult to do. So animal experiments would be also useful, but in humans we can obviously go to some experimental designs like language experiments, which are more difficult in animals, and then use laminar electrodes. And I actually expect that it will not work. The reason is we sort of do not really know what we think is neuroactivity. And so therefore the model, the vascular part of the model, the ascending part of the model might be totally correct, but we have to probably also work on the neural part in order to be able to relate a hemodynamic parameter to the neural parameter. So I think even the failure of the model will teach us a lot about how the brain works and how fMRI works. So I'm actually sort of looking forward to learning from the data, the limitations, and to think more subtle on the level of also on the neuroactivity.
Yeah, no, it's great to have a model, and as you say, it'll be improved as you go forward. Thank you very much.
All right, we have another question from Farouk. So you're next up, Farouk.
Hello. Can you hear me?
Yes.
Hi. I have a question because I see a lot of experts in here that I was wondering about. So I see a lot of talk about veins, like ascending veins and the vein artifacts and so forth. But I was wondering about some like having some discussion on the effects of arteries on the gradient echo EPI and other fMRI acquisitions, because I am working a lot on the auditory cortex, and there are a lot of big arteries around there, like bigger than 1 millimeter in diameter. So they are pumping very fast. They have a lot of blood in them, and they are very close to the gray matter. And I was just wondering, with the long readout times, how the effects from the arteries are affecting the layer fMRI signals, or whether this is an issue, or do you recommend some readings on this?
So I'm super glad you asked that question. I don't want to answer it, but I just had a reviewer tell me that I didn't know anything about physics because I said that arteries mattered. And I don't think that was true, because there are inflow effects that we've always worried about in our data. So I want somebody else to talk about them, but I think it's an important question. I'm glad you asked.
I can answer because the two Camils have published a paper 2009 on the physical base of the fMRI signal. So if we ignore obviously things like what Cheryl mentioned, like inflow artifacts, but assume an ideal experiment, even in the ideal experiments, there is a blood volume contribution, which means we have the fMRI signal is determined by the Bolt effect, like oxygenation changes, susceptibility effect. Therefore, we have the strong venous weighting. However, we have also blood volume effect. And this blood volume effect can, especially for big arteries, can be quite significant. So therefore, I think in the tissue itself, I would probably not think that the effect of the arteries is big, because the susceptibility effect will sort of overwhelm the penetrating artery effect. However, for big surface arteries, there might be an effect because of volume changes.
So would it make sense to have a look into the areas, like gray matter areas near very big arteries lying on the surface, then analyze maybe differently or model them differently?
Yes, yeah, I would think that. And also, depending on conditions, arteries do not necessarily have 100% oxygenation, which means there is also, for big arteries, might be also quite a significant susceptibility effect. So this would be an additional thing, in addition to, as I said, for the ideal case, we have arteries 100% oxygenation or 95. The susceptibility effect is not big, but the blood volume effect will dominate. But in reality, people have measured that arteries close to capillaries, arterioles, can have blood oxygenation down to 80%. So then you have also susceptibility effect on the arterial side. Still, I would think sort of our simplified model is still capturing the main component of the sort of distribution of the spatial profile of the bolt signal, but it might not account for all effects, especially if you look at, say, transients and so on.
Thank you.
Can I say something also to this effect? This is the other Camille. But what Cheryl mentioned about inflow effects, these can be very large, especially if you are interested in something like laminar fMRI. You are not doing large volume coverage. You are selecting few slices, and there's quite a lot of territory in the brain that is never seeing an excitation pulse. It's full of fresh, unexcited spins that are actually going to be flowing into your slice, and I think those can be extremely large. The inflow effect.
So doesn't this other Camille, sorry, when you do your modeling and you're considering these inflow effects, obviously, I mean, it has to make a difference whether you're using something like multiband, which I think, you know, most of us use with gradient echo because you're saturating multiple points in the volume versus if you're doing, you know, 2D multi-slice or 3D PI, right? So do you model or account for that in any way?
No, so the model we are using is sort of the idealized gradient echo experiment, where everything is sort of local. And so we neglect arteries, capillaries, or capillaries we consider a little bit, but not fully. And we are not considering acquisition choice like multiband and so on. So they will all play a role in this. But the question is also how tractable it will be by making it more and more complex. So we are not modeling it, but we have sort of already made it more complex by including, which is not published yet, more sort of finite voxel resolution and orientation relative to the main magnetic field. These are already adding more complexity, but other things like inflow or multiband we have not included. And I think at some point we will also reach a sort of a limit of how much it would make sense, because we still want to have a model which is invertible. So if we introduce more and more parameters, it becomes non-invertible, which then would mean in some cases the model will not be applicable because these effects will be so important that they don't average out. I have a question to Cheryl. If nobody has a question at this moment, Cheryl, I didn't see the data so far with the C parameter, with the physiological noise tail. However, it looked very much like gray and white matter distinction. Do you think we can use it for segmentation?
You are reading my mind. Yeah, I've been on a quest for a long time for, yeah, but don't publish that paper before I do, okay?
I don't know.
I think it cannot be used. Like, it looked actually very bad for doing a segmentation, comparing the anatomical data that you would get. I would say.
Here, let's just look at the data, because yes and no. I think it's a little.
I mean, vaguely it can be done, but yeah, doing layer fMRI and having vague segmentation is not good together.
No. I'm not saying bad segmentation. We've been on a quest for like ways to figure out if we're even in the gray matter, because you often don't have any kind of gray matter white matter contrast in your functional data. and you need something. So we've been using that T1 weighted EPI, and I love it, and that's changed my life. But I have some older experiments where I don't have access to a T1 weighted EPI. And as far as a marker that can at least give me a guidance on where my gray matter is, I think this is potentially very useful.
Well, it's probably a useful tool to register your EPIs to your anatomics anyways.
Yes. If a boundary-based registration algorithm saw these data, I bet it would come up with a decent solution. And I hesitated on sharing this because, frankly, I saw this image for the first time myself 2 days ago. Long story. And I hesitated on sharing it today because I'm pretty excited about it, and I want to be the person who gets to publish this first. But if you guys are faster than me, go for it.
So I had a quick question for Cheryl, also about the C tail or the C tail. So it looks like it's, you know, it has a lot of spatial structure, but it seems to imply that the source is some sort of physiologic noise, though. But if you look at the residuals, that map looks very different. Is it just differences in sensitivity? I mean, so if you look at the map that implies, you know, where the physiologic noise is just from the residuals, where the comparing the thermal noise and you know, that map, or not only that map, but the one I think you showed before using the AFNI. Yeah, I guess maybe that map.
Yeah, this is the only one. It was all the same
Yeah,
slot.
so that looks like it's relatively unstructured.
Right.
But oh, this one on the right here. So this one.
Percent Gaussian.
Yeah. So I'm just wondering the reason for the differences between the C parameter and this. If one is sort of physiologic noise, but this is not thermal, this is sort of physiologic noise as well. You know, they look very different though. So why do you think that would be?
Yeah, wow, I don't know. And it's a little amazing to me that, like, I look at this residual noise image, I see no structure in it. Maybe some blurring internally that presages the problems I'm going to have with my image resolution because of G factors and stuff. But I don't see anything in this noise image that suggests that I should be seeing this kind of structure. My only thought here is that this kind of structure is in the part of the model that has less than 5% of the weight. And so just by eye, we're not going to pick it up. I'm going to show you my backup slide, which is the same analysis applied to my really low SNR spin echo data and my moderate SNR GRACE data. And this kind of structure falls apart when you really drop down into the noise. And so I'm still working on figuring out what it really means. But that's what I've seen so far.
Can I raise a sort of a different topic in the field rather than the analysis? It's being touched upon, but to me, it's one of the major limitations in this laminar cortical depth imaging is spatial resolution. And you know, we talk about nominal resolution, we know about blurring and such, but really, this field is dependent on really pushing spatial resolution much higher than, say, typical fMRI is at. And I think that there are several approaches that can be applied and are coming along. You know, I've seen work from Maastricht and elsewhere on segmented 3D EPI that is really improving the resolution. And, you know, there are hardware improvements that are being pursued. You know, new gradient coils and higher accelerations and higher field. But I really am concerned that sort of the optimization point that we're at, that we've used a long time, was 0.8 millimeter, because that, as Cheryl said, that's sort of our hardware optimization point. But really, you know, the amount of partial volume averaging we're getting from gray matter, from white matter and CSF at that resolution is quite high. So I don't know. I just think there are a lot of experts on this talk, and on this conference, and I think that it's sort of, to me, it's the elephant in the room. I mean, I think, you know, Renzo pointed out many different contrast mechanisms. Sure, for flow imaging, you know, I've been in quantitative blood flow imaging for a long time, that field. And yeah, I mean, ASL, you're concerned about inflow, timing, and effects, and all. This will always be true. Will always, depending on the experiment we're doing. but it seems the common denominator of the real, challenge, if you will, in the field, and one of them is getting to higher resolution. So that's my comment.
Yeah, so I totally agree, David. And this is to quote a very famous David Holt saying from 30 years ago, "This is what keeps me up at night." Camille will remember this. I think, the problem is everybody says, "Oh, I have 0.8 millimeter resolution," but as Cheryl pointed out, I think you really have to report your point spread function for any data to be meaningful, and point spread function is not mentioned in virtually all the layer fMRI papers that Renzo showed in his little montage at the beginning, for example. And it's significant. I think my student Olivia's on here somewhere. I mean, she's done simulations for some current, multiband gradient echo, high resolution with a head gradient. And the point spread function is, roughly a factor of 2 worse than your voxel resolution determined by your matrix. But that's a dirty secret that nobody ever seems to discuss.
Well, I'm an expert on blurring with 3D Grace, and we have new methods coming out that affect point spread function, et cetera. But I think we're all sophisticated enough in this group that we know when we talk about resolution that I'm not disagreeing with you, but it's really still comes down to fundamental real resolution of the voxel. And if we're looking at real 0.8 millimeter isotropic resolution, I think that still is insufficient to doing a large amount of physiologic and layer fMRI we want to do.
Oh yeah, absolutely.
And of course, the voxel size is kind of a weirdly convoluted sequence parameter that can be traded off with like TRs or coverage or anything. And then you gave Maastricht a lot of credit with the segmented 3D API. I see Rudi Stirnberg here in the call, who like we are collaborating with and using his segmented 3D API by trading off TRs in going to very high resolution. So it doesn't come for free. And I think we need to have a discussion on like how much SNR do we need and how much can we offer in order to get to that resolutions that we need. So it's a question of having a signal or having a high resolution signal. Where do we want to be on that trade-off?
So Renzo, didn't you? I mean, haven't you always said that it's the threshold is something like an SNR of 20:1 is what you can actually reasonably, if you average for like about an hour, extract enough signal from. So and then usually that's about at 0.8 at 7 Tesla with the right coils. It's about 20:1, right? So I mean, yeah, I think the key thing is to try to get higher SNR, and also of course worry about resolution. But we're kind of at that limit right now, right?
I guess I wanted to add a couple of things. So first of all, we should also distinguish between image point spread and functional point spread. So what we measure as a function sequence and what Amir Shmuel first published in 2007. We're actually looking at how fast, for example, if we can estimate the edge of in retinotopic space of a specific stimulus, and we expect with infinite precision to see as soon as we move 1 voxel away or 1 centimeter away or 1 millimeter away from the edge to see no bolt signal. We actually care about how long it takes in terms of space to get back to baseline. So these are actually people, when neuroscientists talk about point spread function, that's what they mean. When physicists talk about point spread function, they're talking about what you guys were talking about. And I think that one problem here in the field is that we still do not even agree on, we use the same word interchangeably where we're having different concepts. So that's another super important point, I think, to address. And the other thing is, yes, sure, SNR, resolution, that's super important. And people tend to say, oh yeah, gradient echo is the one where we give up the most of our functional resolution or even image resolution. Therefore, we should do spin echo or we should do some other methods. I mean, these are all obviously, as we all know, and I don't presume to argue with any of you guys on this panel because you all have a lot more experience than me. But what's the point of having infinitely precise resolution if run-to-run consistency is super low because of SNR, and then we cannot get the SNR that we want? So, and that's the graph that I was showing, which was actually produced by by Renzo. That's where I was trying to get at. Yes, resolution is super important, but it's useless without SNR, and vice versa. We've got a lot of SNR if we don't have the resolution. It's also super important. So these are all, as Renzo also pointed out, extremely convoluted arguments that we really need to think about and try to agree on to move forward.
Can I ask a completely different question as an outsider? So there's, it seems to me that people have largely looked at auditory and visual primary cortex. And I'm wondering, I mean, there was actually a recent paper which did, I think it's like Big Brain 3D, where they went through histology of the whole human brain, and where even basic things like cortical thickness, the patterns, how they change across hierarchies are different between sensory and motor. There's obviously gigantic laminar organizational differences between sensory cortices and motor cortices. So I guess in the big picture, are people worried about that? Am I missing like some big part of the field where people are starting to think about these issues?
You know, V1's the only area that matters, and so I don't think that's
right. Well, right. I guess if everyone feels that way.
I guess, and again, like maybe Renzo or anyone else will be more knowledgeable than me to answer this question. But I guess one of the issues that when we're doing laminar fMRI, we are in an SNR starved regime, and you know, V1, visual cortex, especially with surface coils, is where we get our highest SNR. Motor cortex is also where we get highest SNR. So from a like technical aspect, like, you know, studying these areas are easier than study like, you know, subcortical structure or something like that. So that's one motivation I would think. The other thing is, you mentioned auditory. So it's either like driven by the need for SNR or driven by the research question. And most of like the human cognitive neuroscience, they either care about auditory or visual some sort of interaction between the two. Well, I don't know if that's fair to say, but definitely we know that, like, as I was saying, like talking about like the SNR, if you want to do like anterior temporal or frontal or whatever it is, it's difficult enough to characterize the signal in those areas with standard resolution fMRI. So I'm guessing that more or less motivates the focus on visual and motor more than auditory.
People are definitely worried about this question, that the general canonical microcircuit of feed-forward feedback is not applicable to the entire brain. Like in Peter's lab, we did dorsolateral prefrontal cortex or motor cortex where those models are not applicable. There are other simplified models. And I guess the layer fMRI field is like, underscores the importance to find out these models in these higher order associate areas too. We're definitely worried about those. Yeah.
Yeah, worried is probably too strong word. It's just the stage of the field. The field is relatively new. And so the people who were working in this field were mostly methods-oriented people, even though, as Renzo pointed out, and also Luca, more and more applied projects are coming in. So I would not frame it in the words of worried or something like this. I would say it's a developing field where it will be more and more applied outside of these standard areas. And it will sometimes will work, sometimes will not work, and we will learn from the failures. So therefore, it's a normal development of a scientific field, I would say.
No, that's fine. It's just that the presentations often say this is the laminar organization, or this is the laminar pattern, and there's a lot of brain out there, and I guess. And there's a lot of reasons to think that may or may not be true in other places on the basis of just histology and microvasculature differences. And so I guess that's why I use the word worry.
No, I agree with that. But in my CMRR this year workshop, last year's workshop, which I did remotely, so I was pioneer in that. I actually said what we need is area-specific microcircuit models. So it was sort of a, it's recognized by the field that it's sort of, we make two simple assumptions about how neuroactivity is actually organized. But again, for me, this is sort of a very normal process. We develop something, we learn from it, we then question our assumptions and we take the next step. So therefore, for example, the big brain will be a very good resource actually in that process. And I will be, for example, hopefully collaborating with the big brain people in going in that direction. So for me, I think we have to sort of also be careful not to be too negative because it's a progressing field. So if we say these are the limitations which I recognize. It's not that the field says, no, we are perfect, nothing will ever develop. No, the field itself recognizes on all aspects like spatial resolution, registration, analysis, all these choices that we have to make progress. And for example, one of the things what I think will be very important the next decade in laminar fMRI will be connectivity analysis, which we also didn't do so far. But again, that's not a criticism of past projects, but it's the next step in our evolution.
So if I might add as well, I mean, you know, even to take a step back, I mean, realistically with fMRI, we're only getting 3 or 4, you know, segmentations of a layer. And even in motor cortex and visual cortex, you know, there's many more differentiation. So we're probably missing a lot or partial voluming a lot of functional connectivity that might be very significant. So, but we're doing the best we can. And, you know, at least in those, we're correlating with electrophysiologic data. But as Camille implied as well, that, you know, I think with other areas, like for instance, in our work with dorsolateral prefrontal cortex, you know, we found clear upper and lower layer differentiation based on a specific task modulation. And so we can make a best guess as to what those were doing. I think that the field will progress like that. You know, you have these looking at either resting state connectivity to look at which layers correlate to which other layers. And then also with clever designs of tasks, you can actually imply directionality and then try to sort of build a model from some sort of convergence that way. I mean, it's this unknown territory. And you know, and also, of course, put in electrophysiology where we can. We could collaborate a lot with monkey experiments where people can insert the electrodes and see what is the output and what is the input and look at the histology and things like that. So just slow progression.
I would like to ask something regarding the last comment from Camille about the, I mean, from Peter as well, in regard to the maturity of the field. So, I mean, I will expect to see, of course, more clinical applications of the field in the upcoming years. Therefore, I'm kind of curious about the opinion of all the experts present in terms of modeling, for example, specific vascular pathologies at the laminar level. Does it actually make sense to, for example, have like different models across the cortex when we are thinking about, for example, performing connectivity analysis in pathology in populations with a specific pathology that might affect vascular response or vascular reactivity?
So is the question to me?
Yeah, you or anyone who would like to contribute to.
In terms of the model is sort of relatively neutral what kind of vascular organization it is, because these are differential equations derived from mass balance principles, which means it doesn't assume how the blood volume, for example, and vasculature density is in the tissue. The only assumption which sort of would affect the physiological vascular part of the model is the flow direction. So because we are assuming that at the end, mass balance says something goes in, something goes out, and we are just counting what's going in and what goes out, and describe it with differential equations. So if we do not account correctly the sort of the sources and the sinks, then the model will not work. It can be very easily corrected by correcting the source and sinks, but it is based on that assumption. So therefore, if you say I have a vascular disease and the capillary density is different, that's very easy because that's a free parameter which you can just account. So therefore, the model itself is very neutral to brain area, to densities you have. It's all sensitive to the source and sinks accounted correctly. And so for clinical pathologies, the model can be easily applied, and also for brain areas. So there's a sort of misunderstanding that it's because in the paper we assume certain, for illustration purpose, certain blood volume distribution. It's dependent on that. The equations themselves are independent on any specific distributions. As long as the source and sinks are correctly accounted for, the model cannot fail, because its mass balance principle is sort of conservation of matter. So that's a physical principle, and from that point of view, it cannot be wrong as long as you account for the source and sinks correctly. Okay, Esther Kuhn has raised hand.
Yeah, thanks a lot. Because this is exactly the aspect I wanted to ask you about. So in terms of adjusting the model to individual variability, or to individual variability between brain areas, would you actually suggest time of flight, for example, as an in vivo measure? Or how would you try to estimate this?
I think time of flight would not work because we don't have the resolution for that, because we would need the tissue blood volume distribution. However, people are looking into things like resting state fluctuations over the depth and or some vascular challenges. So you could do hypercapnia, and so at this, I'm not pursuing it, but in order to get this kind of parameters, you need additional data. But there might be many different ways, and perhaps clever people will come up with new ways of doing this. In the meanwhile, while we don't have the information, I would always recommend to do sensitivity analysis. So if you make a statement and you say, we found feedback after spatial deconvolution and so on, affecting this layer, I would do sensitivity analysis whether by changing, for example, the blood volume distribution, the same conclusion would come. For example, in our paper, we found that actually if we vary the weights, which are sort of depending on the vasculature, the main features of the profiles were remaining the same. But for other experiments, it might not, for other data might not be the same. So I would think as long as we don't have the sort of calibration, sensitivity analysis will be important. But I think sort of driving this calibration parameters in vivo will be at some point possible. I don't know exactly how to do it at this moment.
Okay, thanks.
Any more questions or even comments? And don't be shy. Well, if there's nothing, I'd like to make maybe another comment. I like to go back to the idea of like the resolution, the true resolution versus the nominal resolution, whichever that may be. And again, it'd be more like a comment stroke question. I mean, every time that we talk in like informal settings or to people, and we're always, everyone seems to agree, oh yeah, that's not true, that there's no one single winner and there's a protocol for data acquisition, and no one says, oh yeah, gradient echo is useless. But then when we see papers, it's a different story. We don't know who's giving comments and stuff and say, oh, gradient echo, you cannot do layer gradient echo, you don't have resolution to do that. So it'd be good to, as I said, like we would like to distill have to be like an interactive environment. And one of the things it'd be good to get like an opinion and a real feel for the community, how the community feels about acquiring data with gradient echo versus spin echo versus Grace versus laser, other than obviously Renzo, we know Renzo's view and mine. But are you guys generally very strongly opposed with to to get an echo sequences because of the blurring, or do you think that the SNR gains are motivation enough to keep acquiring data we get an echo and then using post-processing strategies to maybe circumvent or understand what we're doing and what really we can conclude? So open question to the floor. Having your opinion on this would be very useful.
I thought Renzo's comment about the matching to experimental design is something that's extremely important. And I think maybe it's not even talked about enough, is that, I mean, it's not just choosing the right sequence or the right paradigm for what you want to study, but matching them is probably the most important aspect there. And I think that, yeah, I think that that's a really important aspect of how we go about laminar experiments, is not only trying to decide how to best measure the different layers and how to get the best SNR and effects in different layers, but also really importantly, choosing our paradigm so that we're actually modulating the layers in the way that we think we are. And I think, like Camille has said, that's a process that's probably going to take a very long time to try to work out exactly how to modulate things the way that we think we are, because we're probably not.
This is David again, and I guess I just want to maybe not clarify, but expand a bit. You know, on the resolution question as a parameter, absolutely, of course, we're talking about sufficient signal to noise, and there are always trade-offs, as Renzo mentions, between, you know, field of view and TR and all these things. But you know, my experience of a different field, which was you know, blood flow imaging in the, you know, in the 80s and early days, there are many different methods: time of flight, Fourier velocity imaging, velocity phase imaging. But what came out eventually was a technique that seemed to separate out major confounds in the imaging parameter that you wanted to look at. And that was a subtraction phase contrast was what it was called, but velocity phase contrast imaging. You know, it got rid of a lot of the background phase errors and such. And so I sort of look at the venous, the draining vein issue as sort of a confound in what we're dealing with now. The complexity of functional imaging goes way beyond quantitative velocity imaging, or what we talk about now as you know, blood flow imaging for clinical and other applications. But I really think that the field is, I'm seeing, because I'm more of a methods person, and yes, I review papers and collaborate, and I really see a lot of advancement and maturity in the different techniques. And I do believe that there will be sort of preferred methods to use, be it VASO or other techniques, depending on whether you want large field of view or a specific area. And I don't know, I think it's a really important part, because if you're looking at modeling data like Camille Uladog is doing, you really want to have data that you're putting in that you understand, you know. And that was true in the ASL field too. I mean, you know, the blood transit time or inflow time became a very important, not just the actual ASL perfusion measurement, and actually ended up having a lot of clinical value. So I think that everything advances together, but I really think that the imaging and knowing what you're looking at, and particularly with cortex and looking at, you know, we talk about layer fMRI, but it's really depth dependent fMRI. We're having so much partial volume averaging, we really aren't looking at layers. And yes, we can't really study the physiology between the layers if we can't resolve them. So that's my 2 bits, I guess, you know, my bias in my work.
To take the biological perspective of that, David, and I think you're completely right. I mean, so, you know, historically, when you looked at how electrophysiology was used in the brain, you know, you put a single tungsten electrode in and you measured from all the layers and you made your neuroscience theory based on that. And then people started having laminar electrodes, and so they had to revise all their theories. And now we have laminar electrodes that are available in matrix electrode form, so you can do depth and cortical extent, so you can look at layer connectivity and things like that. And so theories get revised yet again. And of course, optical imaging does that too in the first few layers. So the trick with laminar fMRI, which is an aspirational title, it's not true in the least. It's depth dependent fMRI right now at best, I think accurately. So I think, you know, if we want to come up with theories of how the brain works based on fMRI, with whatever techniques we're currently using, gradient echo, spin echo, Renzo's approach, any of these things, you need to be aware of the limitations. And there's a lot of unknown areas where people haven't stuck electrodes in human brain. And so in those areas, fMRI can't be compared against anything, while as in A1 and B1 and S1 and so on, we do have electrophysiology. So I guess we have to validate against the very high resolution techniques in the first instance, before we can extrapolate to the terra incognita, you know, the working memory areas and places like that where we know very little about. But I think you always have to bear in mind the limitations of the technique before coming up with new theories of neuroscience. And I think that's always the danger that I think you have to be very careful about.
Yeah, I guess I know, I see your point, that there's evolution in measurement techniques, but in my experience in the MRI imaging field, better is better, and it tends to win. It tends to win out, whatever the parameter is, and I just see a huge advancement compared to what, you know, in terms of the sequences and what we can achieve now in terms of imaging parameters compared to, you know, in the early 2000s, you know, when we were using techniques and we're doing 0.8 millimeter resolution. I just think that it's something that we should strive to emphasize in the field. And, you know, we need to advance the techniques for everyone, the technology, the sequences, the hardware. And I know that everyone will continue to use whatever they can get their hands on their scanner. But I just think that the field is, like you say, you know, all these theories will be, maybe I'm wrong. Maybe the theories that you can come up with 3 measurements across the cortex, maybe we won't do better than that with fMRI. I don't know.
I just want to like make a small comment as well. It looks like I'm talking all the time and just trying to fill the blanks really. It's just not a great technique, but yeah. I mean, for me, like I'm coming from like a neuroscience background, cognitive neuroscience background, and in the field of neuroscience, especially when you talk about real like hardcore neuroscientist, animal electrophysiology, as soon as you talk about laminar fMRI, they cringe. And I completely agree, and I completely agree with what both of you guys have mentioned right now. We can talk about cortical depth-dependent fMRI at best. We don't know partial volume. We don't even know the location. The partial volume is an issue, but we don't even know the location of of the layers in the cortex. There's no way to assess the quality. We're talking about equivolume, equidistance, and all different types of computing layers, but we still really don't know. So cortical depth dependence at best. However, and as I said, like in the field of neuroscience, people take this very, very seriously. When we move to the field of like maybe MR physics and stuff, maybe it's a little bit different. And my understanding was that when we talk about laminar fMRI, so followed by fMRI, we're actually talking about cortical depth dependent fMRI. So I'm starting to use the two interchangeably right now, and maybe that's not a good thing. So that's another thing that we should agree on, like as a community. When we talk about fMRI, even if we talk about layers, we're actually talking about cortical depth. So maybe that may help clarify a little bit the confusion, just like a comment.
Yeah, I felt like in the interest of ending on a happy note, since we're pretty close to ending, that we're definitely not seeing layers. But we've gotten to the point where we believe that we're definitely seeing different things through depth. So as long as we're honest with ourselves about, we're not seeing layers, but we are getting a new dimension to the information. We don't yet know how we're going to use it, right? But I think we've gotten far enough to be pretty confident that there's something different going on in those deep voxels and those superficial voxels. And just that is enough to move neuroscience forward some. And then, you know, eventually we'll get big enough magnets that we can move forward even farther.
That's a very good point. I agree with Cheryl. I really think it's an exciting field given what we can see right now.
Oh yeah, I mean, don't get me wrong, I would also like to end on a happy note, especially these days. I mean, I think the analogy is astronomy, and if you look at what's happened with optical telescopes in the last 20 years, with adaptive optics and things like that, the ability to resolve you know, things that we thought were, you know, singular objects that actually are multiple objects and so on. You know, they've refined science, and maybe in some cases they've revolutionized science. And I think with MRI, which has a lot of commonalities, certainly with radio astronomy and interferometry, you can imagine similar kinds of advances over the next 10, 20 years. So I think there's a lot of opportunity here.
All right, thank you very much. And then I guess if no one else has anything to add, we can bring this first meeting to conclusion. Thank you very much to all for joining. We're super excited about this, and hopefully that wasn't too clunky. It was our first experience with online meeting with so many people. And again, thank you all very much to the speaker, for the talks, and to the attendees for the beautiful interventions, and hopefully we'll keep this going and the community growing. So again, thank you very much. This is it for today. Please follow us on all the medias, and please get in touch with us for suggestion for the following meeting, and we'll do the same. We'll keep bugging you too, so don't worry, you're not gonna get rid of us.
Good job, guys.